All right, section 9.5 is all about counting subsets or combinations. So we looked at a construction of elements in a set before. We called them R permutations. These are combinations. So there are two things to look at here in this section. The first is what the heck a combination is. And the second is distinguishable. Distinguishable, that word always looks fake to me, versus indistinguishable. Objects or elements. So let's start with the definition for combinations. So we are going to let n and r be positive integers or 0. So they're in z plus union 0, such that r is less than or equal to n. And R combination of a set of n elements is a subset of R of those n elements. And is denoted it's a stack and stacked over R, and we define this as n choose R. Right, so some of us might be familiar with n choose R, and what this is the number of subsets of size R that can be made from n elements, or from a set of size n. So the difference between combination and permutation is combinations look at subsets, whereas permutations looked at orders, and they are related. So we're going to walk through that relationship. They're not isolated. So remember, permutations dealt with factorials, and combinations do as well. So n choose R is defined as n factorial over r factorial times n minus r factorial. Now you'll notice, if you're keeping up with your lectures, this piece right here, this is our permutations. This is our R permutation out of size n. And this is, or in other words, this is P of n comma R divided by R factorial. And so a lot of times we see the formula for n choose R as P of n comma R over R factorial for 0 less than or equal to R less than or equal to n. So this is how permutations and combinations are related. There are always less combinations than there are permutations. Now the classic example for combination is splitting people up into groups. So at one point or another, every single math student gets asked, how many different ways can I group people up if I have this many people to choose from? And so that's what we're going to do. We're going to, a couple examples like that. So how many groups of 5 people can be made from 12 people. And we want distinct groups. Well, this is how many combinations of 5 people can we make? Or in other words, if you have 12 people, I need to choose 5. So we call it 12 choose 5 or n choose r for a reason. You have 12 and you're choosing 5. So this is 12 factorial over 5 factorial times 12 minus 5 factorial, or 12 times 11 times 10 times 9 times 8 times 7 factorial over 5 factorial times 7 factorial. Remember, we're always looking to cancel the largest factorial we can. And so this is 12 times 11 times 10 times 9 times 8 over 5 times 4 times 3 times 2. So 5 and 2 go into 10, 3 goes into 9 3 times, 4 goes into 8 2 times, and we end up with 792 different groups of 5 we can make. So this isn't as common because there are usually restrictions placed on grouping up items or elements or people. So let's say we have 2 very particular people and they insist on working together. So how many groups can we make now? So you should be thinking about, should this be less or should this be more? So think of that for a second. Pause the video if you care to and think, is this less or more? The answer is this is less because there's a restriction. Anytime you place a restriction on something, there should be less options. Otherwise, it's not a restriction. So we're going to say person A and person B work together. So you can kind of think about this as when we do our proof by cases, this splits us into 2 avenues, right? We can either have a group that has A and B, or we could have a group that doesn't. Because our restriction is that they insist on working together. So if I pick 5 people out of 12, I don't necessarily need to pick them. I don't need to pick these 2 people. So let's say scenario 1 or case 1, we have a group has A and B. So we know that our groups are going to be an n choose r, so what we want to be thinking about is how many people are left now and how many people need to be selected into their group. If 2 are already there and we're still making groups of 5, that means I'm only choosing 3 more people to join them, and I only have 10 options left. And this would be 10 factorial over 7 factorial times 3 factorial, or 3 factorial times 10 minus 3 factorial. And this is going to be 10 times 9 times 8 over 6. This goes into 9 3 times, goes into 2 4 times, and we end up with 120 groups that could have persons A and B. Case 2 now is we don't have A and B in our group. So a group does not have A and B. So now we're still selecting from 10 people because A and B are excluded, but we need to pick 5 new ones now. And so this will be 10 factorial over 5 factorial times 5 factorial, or 10 minus 5 factorial. And so this will be 10 times 9 times 8 times 7 times 6 over 5 times 4 times 3 times 2. So 4 and 2 go into 8, leave nothing. 5 goes into 10 and leaves 2. 3 goes into 6 and leaves 2. And when all said and done, we have 252 options here for a total 120 plus 252, 372 options. So we have a lot less choices versus we can group any 5 people together. Now imagine we were more prohibitive on our restrictions. We would have even less options. So what I would like, or what I would have had you try, is now suppose 2 people hate each other and refuse to work together. How many groups of 5 can be made from the 12? So please do pause the video here and try this out on your own. Think about it. Think about what your restrictions are. And then unpause and take a look at what the solution is. And I'll start going through it now. So we have 3 cases in this scenario, because what we have is not A and B. Now, logically, this means a couple of things. We know that this is equivalent by De Morgan's law to not A or not B. And so that gives us our 3 cases. So we can have A and not B, in which case we have 10 people to choose from because A is in our group. We can't have B, that eliminates 2 choices, but we need to pick 4 people, which is 10 factorial over 4 factorial times 6 factorial. And this is going to give us 210 options. We could have B and not A. And this is the same. We have 10 people to choose from now because B's in the group and A cannot be. But we have 4 more to choose. So again, this is going to be 210 people. And then we have not A and not B. And so this is only 10 choices because neither of them are in the group, but we still need 5 people. So 10 factorial over 5 factorial times 5 factorial, which we know from previously is 252. So our total becomes 210 plus 210 plus 252, or 672 choices. Now you look at this and you say, why is this more than the last example? Why are there more options this way? Well, think about the restrictions. Think about the number of ways we could do this. In the last example, it was either with A and B or without A and B. So we either had to choose from 10 and choose 5 people, or we had to choose from 10 and only choose 3. In this scenario, we're restricted to only 1 at a time or neither. So while there are more cases, this is actually a less restrictive option because it allows for more wiggle room. So one of the big issues here with people, it's obviously not an issue because no 2 people are the same unless they're clones. Clones don't exist though, so we don't have to worry about it. Distinguishable objects is a really big problem in ordering and counting in mathematics. And we can look at this example to see why. So how many distinguishable orderings of, the classic word for this is Mississippi, 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 are there? Now, why do we choose Mississippi? Because it has a lot of repeated letters. So we know there are 11 spaces, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 spaces that we can order up. And the big issue is S has 4 copies. So if I put an S here, you cannot tell if it was this S or this S or this S or this S. So once we choose the spaces for the S's, we can move those around in any location. So if there's an S here, and here, and here, and here, for example, I can switch all these around as many times as I want, and you can't tell the difference, because S is S is S is S. They're all the same letter. So once the S's are chosen, or placed, we can move them around. Exactly 11 choose 4 ways, because we have 11 spaces and we have 4 letters to place. And so we can place them anywhere we want. This is one configuration, one example. And so there are 11 choose 4 different ways that we could place S's first. So once you've done the S's, the next letter that repeats the most is the I's. There are 4. So if the S's are all positioned, or placed, then there are 7 spots left and 4 I's to choose from. So 7 choose 4 ways to place the I's. And that means that there are 3 spots left, and we can place the P's, all 2 of them, exactly 3 choose 2 ways. And then 1 choose 1 way to place the M. And the way that this works is, since we could do this in any order, this is multiplicative because each is a successive choice. It's not this and then we stop and start again and do the I's, and then we stop and start again and do the P's. We do the S's and the I's and the P's and then the M all at once. And maybe we do M and then P's and then S's and then I's, but it doesn't matter mathematically where you start because there's really only one way to choose. And we'll look at a couple relationships. Well, actually, in the next section, we'll be looking at some relationships for combinations that kind of dictate why things are equal in 9.6 and 9.7. So for now, this is successive choices. They all happen in the same event, so to speak. So that means we multiply 11 choose 4 times 7 choose 4 times 3 choose 2 times 1 choose 1. And then we're just multiplying that out. 11 factorial over 4 factorial times 7 factorial times 7 factorial over 4 factorial times 3 factorial times 3 factorial over 2 factorial times 1 factorial times 1 factorial over 1 factorial. So obviously those cancel themselves. 3 factorial cancels with this 3 factorial. 7 factorial cancels with this 7 factorial. And we end up with 11 factorial over 4 factorial times 4 factorial times 2 factorial. And if I've done my math correctly, this becomes 3,850. So that's how many distinguishable ways we could place the 11 letters. So remember, successive choices means multiplicative. So there's a really important theorem that gets linked into our combinations and permutations. And it says permutations with sets of indistinguishable objects or it talks about permutations with sets of indistinguishable objects. So it says, suppose a collection of n objects with n1 that are type 1 and indistinguishable, you know, for as lazy as I am, I think I'd have a better abbreviation for indistinguishable. N2 are type 2. And indistinguishable, I'm going to abbreviate that way. And this continues on. You keep counting your n sub k are type k. And indistinguishable. And n1 plus n2 plus ... plus nk equals n. Then the number of distinguishable permutations is n choose n1 times n choose n2 times ... Oh, scratch that. It's n choose n1, and then we lose some of the choices, so it's n minus n1 choose n2, and then it's n minus n1 minus n2 choose n3, and this continues on n minus n1 minus ... minus all the way to n sub k minus 1 choose n sub k. That's what we did in the last example. Every time you lose the number of choices that were the type before, and this turns out to equal n factorial over n1 factorial times n2 factorial times ... n sub k factorial, which is exactly what we saw in the last problem. So if we flip back to this, we had 11 letters, 4 repeats for S, 4 repeats for I, 2 repeats for P, and 1 repeat for M. And our final answer that we got, 11 factorial, which is n factorial, over 4 factorial, 4 S's, times 4 factorial, 4 I's, 2 factorial 2p's, and 1 factorial is 1, so I just didn't write. But there is technically a 1 factorial hiding there. So that's exactly how it works using this theorem. So knowing what we know, let's look at a more complicated example. Let's suppose there are 5 men and 7 women, and they are split up into groups of 5. How many groups contain 1 man? So here's the issue that arises. So most people think, okay, I have 5 men, I can choose 1, and then it doesn't matter out of the remaining 11 people how many I choose because I have 1 man. And we choose 4. Well, the issue that we get from this example, so I'm telling you now this is incorrect, and why we need to use different result. Let's say man 1 is chosen, and then the other 4 people are man 2, man 3, woman 1, and woman 2. Right. Well, another selection could be man 2, and then man 1, man 3, woman 1, and woman 2. These aren't different groups. Yes, we chose the initial man that made it part of the 1-man groups, or that contains 1 man, but these groups are exactly the same, and these are counted twice in this situation. This is why we have to use the distinguishable permutation theorem, because we need to be able to not count this group again. So yes, there are lots of ways to do this, but this is why that theorem is so important, because something like this happens and we count the same thing twice, because mathematically this is a quote-unquote different group because it started with a different selection. But that's not what we wanted. So that's the reason for that theorem, and this is the end of 9.5.